Hello, this is Siddharth. Today we'll discuss about a topic of decoupling the diffusion transformer. This is a paper demonstrated few weeks back. Today we'll try to discuss what is the problem and how they are solving it. If you see this, the major problem for this is you have a lot of limitations in the unified architecture, right? Let's understand what is unified architecture. Unified architecture is nothing but a single point of brain which is trying to do multiple jobs, which means you have a one module, it will handle two different jobs. And this limitation is particularly they are talking about in diffusion transformer, where they will use this particular model for the image generation. And let's also understand what is diffusion here before we go into the paper. The diffusion is nothing but cleaning up a noisy picture which is not so clear. When you're trying to generate an image, it will clean that picture until it becomes a good image. That is all about the diffusion. And now when they have this unified architecture in this diffusion transformer, we have a problem where it could not generate a particular image. In this particular, if you see it here, they have two different types what they want to show it here: the conventional diffusion transformer and also this decoupled diffusion transformer. And in this conventional diffusion transformer, if you see the visual encoder, the pre-trained visual encoder is the only one, and once it takes some input, the diffusion transformer will come in picture to generate that particular image. And when they are trying to generate that particular image, they are getting lot of noise. So to solve this particular paper, they are trying to decouple this. The name itself stays in the paper, decoupling, right? What they are doing it, they have this visual encoder and the separate one. If you see it here, the diffusion transformer is divided into two specific jobs. Once the pre-trained visual encoder is done, from there it has two parts, which has this conditional encoder and this velocity encoder. Now we will talk about it. As I said, if you try to understand this particular problem statement, currently we have a diffusion model where it tries to achieve both tasks by one basic transformer, right? And when you see it, which is single for both the tasks, right? It is trying to get that particular image done also with adding things where to look. So when you do that using this model, you will see this lot of noise things, right? That's the one where they want to solve this issue. And if you see, there is something called noisy data and they have this actual picture. Now let's try to understand what is diffusion transformer, right? In this diffusion models, the particular thing is the model tries to generate the data by just starting with a random noise. Just you can think about the outer line structure, and it will try to gradually refine it until it gets a particular clear image. If you see in this particular image, the first thing you will see something like this noisy kind of thing, and the model will gradually refine it to look something like this. And what they are doing, they are attaching this diffusion model including this transformer, as the transformers are originally designed to process the language and to understand the relation between the two words or sentences or a paragraph, right? That's what these transformers are doing. They want to combine this particular diffusion model and transformer to get a better image. And if you see here, the particular paper talks about decoupling this diffusion transformer and how they are trying to achieve this. They divided this particular unified architecture into two different jobs. One is the conditional encoder and other one is the velocity encoder. The name itself tells you conditioning. This particular object focuses on understanding what is the overall structure. Sometimes you see that artist, if he wants to draw something, he will have just an outline. To before he finishes a picture, he'll try to have that full outline. That is what this conditional encoder will do. It will have that overall structure ready, and what it does, it will have that main elements of the image and having that sketching outside of the basic shape and also this layout. Now once you have this layout ready, the second part, it will come to this velocity decoder. What this does, this part is specifically decoded with the final details. For suppose if you're drawing a human, right, the outer line you'll draw with about the shape of the head and the ears and everything. Once you have that outer layer ready, you will have that ears and the fine tuning, right, the lips and also eyes and the eyebrows and everything. That whole part will be taken care by this velocity decoder. So they are trying to solve this unified architecture by dividing this into two parts, which is conditional encoder and velocity decoder. And if you see this, I just want to show you one of the random example in the decoupling this diffusion transformer. If you see, this conditional encoder will focus on specifically outlining the particular drawing, and this velocity decoder will just have those colors, structuring, and also this minute details, how the house should look like, what color it should be, how the grass, what color is it, how the road is, how the sky should be. Everything is being treated by this velocity decoder. This is the simple way of showing that how they are trying to achieve this particular solution. Now, if you see the second example, the first conditional encoder will just have those particular outline overlay of the picture, whichever you see it here. And the second one, the velocity decoder will just make sure to have this particular full image ready with the finer details. And before we go to the benefits, right, I also want to tell you how this particular experiment has been happened. In this particular diffusion decoupling model, during this denoising process, a conditional encoder extracts the semantic features, as we know, right, from this different kind of noisy inputs. The self conditions guide the velocity decoder in reconstructing the image, right? And for this, to enhance this particular efficiency, the paper proposes sharing self conditioned features between adjacent denoising steps. And however, this indiscriminate sharing can degrade the performance. To address this, the author also introduced a statistical dynamic programming method to determine the optimal sharing strategy that balances inference speed and also this image quality. And let's have a particular analogy how this painting will be so efficient. I'll take an example of a painting. In the initial sketch, you draw a detailed sketch for the first frame, and the next step will be the reusing sketches. For the next few frames, instead of redrawing from the scratch, you reuse this initial sketch and make these minor adjustments. And the third major thing is you need an optimization. You decide when to reuse a sketch, when to create a new one, and also ensuring the animations remain smooth without unnecessary effort. Similarly, in DDT, the model reuses the self-conditioned features between steps to save computation. But strategically, it decides when to compute them to maintain that particular image quality. And if I have to step by step breakdown, right, the first basic thing is denoising the process. What this does, the model progressively denoises an image over multiple steps, like first iteration, second iteration, or third iteration, or so on. Once this is done, it has to do this self condition on whatever the extraction we got it. At each step, this conditional encoder extracts semantic features from that noisy input. Whatever the input you have it, if it is noisy, it picks that actual semantic features from that noisy input. And once you have that, it will also have the feature sharing. The major thing is efficiency, right? To improve the efficiency, the model reconsiders using the self-conditioned feature from previous steps. And also you need to understand there should be an optimization challenge also for this. Reusing these features indiscriminately can degrade this image quality also sometimes. So for this, they come up with a specific solution called the dynamic programming. And the model, whichever you have it, it employs a statistical dynamic programming approach to determine the optimal points to recompute or reuse the features, balancing the speed and also the quality. And using this, there will be some major benefits we need to speak about it, right? The first main thing is faster inference. By reusing this particular features, the model also reduces the computational load. If you don't reuse these features, what happens? You need to do every time from the scratch. It will have a highest computational load on the system, which it will take a lot of time to get this particular result. And we should also understand it should also maintain a quality. Using this particular architecture where you're dividing into two different tasks, it will also help us to have a strategic recomputation, and this will generate the high quality image. Even you try to do multiple times, you will maintain the same quality. And before we even try to decouple also, we need to remember something in mind. Whatever we are trying to do it, at the end of the day, the performance should be optimized. For this, as we already know, they came up with a particular approach called the dynamic programming, which it finds a better solution between this particular speed and also the quality. So this is the total benefits. And I just want to have this a short explanation because I don't want to go through the details. If someone likes it to go through this particular details on how the experiment is being happened and what are the results, please let me know. I can have that from the next sessions. Thank you. Until then, bye. Please don't forget to share, subscribe, liking it. It will be so much beneficial for me. Thank you.